Good morning. We're gonna give it today. I try to find out how using the state space matrices we can find any transfer function. So this will require some mathematical operations with matrices so that we have the ability to find any transfer functions if we know the state space matrices. So that's our objective today. On the screen, you see the regular state space form of the equations in first order. You have the state variable vector is x, the derivatives x dot, the inputs u, the outputs y, and of course you have the A, B, C, and D matrices. So let's see what we can do now. Let's disappear from here. And first of all, let's identify what we want to do. The very first thing is, what is a transfer function? And I am going to write it down in here as a transfer function. By definition, what is this? Transfer function is always a relationship. Relationship between one input and one output. Okay, so this is true over here. If we identify the outputs in here, can we identify the outputs in here? And this is the outputs right here, and this is the input right here. So it follows, if we could say, transfer function would be a relationship between the outputs, which is y, in relationship to the inputs, which is u. This is what we are after. Okay? So we need to use these equations in here to be able to achieve this transfer function. And in this case, what I want you to recognize is that when I am talking about the vector y, I am talking about several outputs, right? And I am talking about the vector u, also several inputs. You see what it says? Here's the relationship between one input and one output. Yeah, one input, one output. That means if I have two outputs and I have one input, I get two transfer functions. But if I have two outputs and two inputs, I will get a relationship of each one of those outputs to each one of the inputs, so I will get four transfer functions. That's what this means. So in order to get this relationship, it seems to me that we have, strategically we can look at these equations and then say, hey, I have this output in here and I have the input in here. And I just need to find out how to get rid of this x to create this relationship. So what are we going to do is use we have to use both of these equations. But at the very first step that we're going to do is to apply the Laplace transform to the system of equations. So when we say apply the Laplace transform, and that is in here you will have, let's see, on the first one, we apply it to this would be S. Remember, that the dt is the operator S, that's the Laplace operator. If we apply S times x of S is the first one, and this is going to be equal to A times the x of s, like this, plus the matrix B times the output U of S, right? This is the application of the Laplace transform to the first equation. The application of the Laplace transform to the output equations, you would have that Y of S is equal to C times X of S plus D times U of S. Yeah. So using the first equation, I could move. See, these are common terms. That one and that one. So I could write down, and I won't save any steps so that everybody follows me. And then we'll say minus the matrix A times the vector x of s, like this, equals to the matrix B times the output vector u of s. Yeah? Now that we have done this, then it follows that we can use this common factor x of s. This is a vector here. This is a matrix. Both of these need to have the same dimensions. So the way we're going to do this, we're going to say this S, if I multiply by the identity matrix minus A, then we can actually take the common factor x of s out and express it as I am doing it right now. Okay? But you see, once we have it here, we really need this x of s to be able to use it on the second equation. Let's just put some numbers. Let's call this number 1 and let's call this number 2 so that we have a good reference. If I multiply this by the inverse of this matrix, like this, what would I obtain on this side? And what would I obtain on the other side? And this is like Si minus A, like this, inverse, and then B, and then U of S like this, yeah? What is this? If you multiply the inverse by a matrix, what do you get? This is a basic operation. You know, isn't it true that if I have the matrix A times the inverse of A, I get the identity matrix, right? So this is the same thing as writing the that x of s like this is equal to Si minus A inverse times B times U. Yeah? Now, if I use this in, you know, we use x of s in equation 2, then what do we get? See, we use an equation 2, you say y of s vector is equal to the matrix C, and now we substitute this into here, would be Si minus A inverse times the vector times the matrix B times U of S, and then plus D, right? Plus D multiplied by U of S, like this. This is from this. So all I did is I put this into here, yeah, and that's what I come up with. But you see, now we can factor this on the on the right hand side. Y of S like this is going to be equal to matrix C times Si minus A inverse times matrix B plus D. And this whole thing would be multiplied by U of S, like that. See? So we can very safely write the end result of our derivation here. I'll write it with a different color. The relationship Y of S over the input U of S is actually this product of matrices C multiplied by Si minus A inverse times B plus D. Excellent. So if we have the matrices, it follows that any transfer function can be calculated by using the state space form. So the conclusion is, I think we could just say conclusion. You could say, if we know the A, the B, the C, and the D matrices, then, let's just put then, Y of S like this, over U of S equals to what we have in here, the matrix C times the Si minus A inverse multiplied by the matrix B times the plus the matrix D. Any of this, if we know all the matrices, this would allow to find any transfer function. So this product of the matrices would allow to find any transfer function. So in order to for this to be effective, what we need is to define the outputs, right?